Okay, so now this work instead is done in the context of MAX, so Materials at the Exascale, Center of Excellence. And title is Optimizing Electronic Structure Codes for KNL, Lights and Shadows. So I will give you a presentation of what was great and in running and profiling, as I said, quantum espresso on KNLs and problems that we found. So for those of you who have a background in material science, quantum espresso and actually PW, which is the code that we tested, is a program to solve the many-body Kohn-Sham equation, the many-body Schrödinger equation with the Kohn-Sham approach, and it uses a plane wave basis. But I won't discuss the details of the physics. Instead, from the computational point of view, the code is mainly FFT and linear algebra. You have grids spread among all the MPI processes, and these grids have to be moved from real to reciprocal space. And the second part is the preparation of the matrix elements of an Hamiltonian that is later solved, and this is where linear algebra is mostly involved. Well, actually also FFT in order to compute the matrix element. So the code as of today is a hybrid MPI plus OpenMP code, but the real parallelization is done with MPI. So OpenMP is only used to improve when the MPI parallelization doesn't scale anymore. And the user is provided with a set of parameters to divide the workload among the various MPI processes. And there are indications to the user on how to do this, but there is no automatic parallelization right now. And finally, the code exploits MKL and ELPA for linear algebra and diagonalization. So the problem that we face, not with KNL, but in general, is that, of course, there is an increasing hardware complexity and heterogeneity, and this is not going away. The solution is to partition the work in kernels and domain-specific libraries, but even after doing that, the problem is that the parallel performances are still very bound to the execution environment. So it's very, well, this is kind of trivial. The real problem is that the performances can change a lot depending on the input parameters that the user provide. You see here the same input file always on A2. This is the change that you get if you provide the wrong parallel parameters. But when I say wrong, I don't mean that you're doing something stupid. You just can work in a memory replicated mode or in a domain subdivision. But if you do one choice or the other, you get a lot of differences. That is no surprise to the developers, but of course a great problem for the users that don't know in general the details of the program. And on parallel computers, they just know the equations and they just want to get the numbers for the equation that they want to solve.
Excuse me.
Yes?
This parameter you refer to some parameter for the compiler, or
Oh, sorry. No.
specific to your application?
No, it's specific to the application. So it's a set of parameters that define how the workload is spread among the MPI processes and how the diagonalization is done. For example, if the reduced matrix diagonalization should be done in parallel by many processes or just by one process. So it's all related to the program. But this has a huge impact on performances, as you can see. But I would say that a skilled quantum espresso user can be more or less, or at least a quantum espresso user can be trained to do something that is not too bad. The fact is that these parameters also change a lot the way memory is used. So, of course, in data replication, memory accesses are much greater, and that is exactly the point of my next slide. I don't know if you can read the numbers. So, so what you see here is the same workload done by one process. The second line is always one process doing the same workload on the same amount of data, and the first line in this table is the same workload on the same amount of data, but done at the same time by 10 processes. So this is an actual quantum espresso run. And you see that there are, well, some cases where this has no effect. For example, just a little effect here, 9.6 against 8. Or, well, no, the other one actually have, no, sorry, 6.2, 6.9. But in some cases, there is a huge difference. So, and this clearly has to do with how, clearly I can say because I know how the program, what the program is doing here, but this is just data replicated simulations done on the same, really same matrices. So the problem is memory access. And this is indeed what motivated the first thing that we have done. So there was an old estimate of the memory consumption done within Quantum Espresso, but the accuracy is what you see here. So this line was what Quantum Espresso was reporting for the memory that will be used in the simulation. And now with the new, we have a separation between the memory allocated at the beginning of the run, which is this red line here, and the peak memory. And this is extremely helpful for two reasons. Of course, as I said, new generator, different accelerators, new generation of accelerator will have different memories. So understanding and providing to the user an information about how much memory is used by this run and where it is allocated, because that's what we do now, is important. And of course, this was the first point to understand how much of the memory used by the Quantum Espresso, how much the memory used by Quantum Espresso compared with the high bandwidth memory available on KNL, and how much we had an impact on performances due to the different approach of memory access. So I have to mention that to do this, the tool GPEF2 were extremely useful because it provides a graphical representation of memory accesses as a function of program execution that is really helpful. Okay, so in the context of a co-design work with Intel, we decided to do this test. We choose a meaningful scientific case, which is one of impurity in a supercell. And we wanted to understand how are we limiting in running in KNL, and turns out immediately that the limit is the memory. So simulation of this 256 atom just takes less than an hour. But we cannot do a bigger simulation because of the 86 gigabytes of memory. So, having said that, this is what we observe as the best execution. So, the best time to solution is obtained with a pure MPI execution. But you do see that, sorry for this, here there are many timers where you do observe, for example, the effect of memory replicated access, this one here, or this one here. But already at 64 cores, we are losing the perfect scaling. And so the question is, how well is high bandwidth memory exploited in this case? And we checked this with VTune, and we found that DRAM is use just a little. So most of the time, the application is not having real access. It's not really accessing DRAM. While same is not true for MCDRAM. And so we are not limited by the bandwidth, I would say. So there is, for most of the time, we are using about 100, 150 gigabits per second. And so the cache mode is really effective, but it doesn't look that the problem comes from MCDRAM. And indeed, the best time to solution, that I said, is pure MPI, has more than 25% of the time spent in communication. So for a problem that can fit the KNL, more than 28% of the time, for the best set of parameters, providing the shortest time to solution, most of the time is spent in MPI communication. So, well, I will go quite quickly because it's late, but well, the solution, of course, was part of the solution was to change FFT, because the current implementation was done on a 1D scatter, 1D FFT, then a scatter of all the elements of the grid, and then a 2D FFT on each core. And this was moved to a 1D plus 1D plus 1D. This case much better for high number of cores. But now we are experiencing the problem of performing the scattering for this 3D FFT on the program side rather than on the FFT driver. So in principle, it should take the same, but in serial executions, this approach takes, or in small cores, this approach takes much more. So finally, a few words on some problematic points. As I said, most of the time is spent in FFT and linear algebra. For this specific input, we have about 60% of the time spent in MKL, BLAS, and FFT. It could be also, so for very small inputs, it's the opposite, but this is a reasonable assumption. Let's say half and a half. It's a reasonable assumption for most of the input files. And so, as you can see here, most of the time is spent in basic linear algebra operations. And so we decided to have a look at how MKL performs on KNL and on Broadwell. So what you see here in blue and orange is the performances of KNL of the various basic linear algebra operations and on Broadwell. So this was done with the idea of moving the code from a pure MPI implementation towards an OpenMP based, or let's say a more significant work towards done with OpenMP. So we checked how the same load running on 4 MPI or 8 MPI processes on Broadwell and KNL, this can be done because of the parallelization scheme. So I can run the same load using different number of MPI processes. So this same load, how the total time that is spent on MKL, how much changes. So DGEM is awesome. Like it performs, it has the same performances on KNL and Broadwell as expected, and it scales very well. There are other routines where this is not so nice, but really, I mean, in our case, it's not really important. And there are situations where, well, this routine here is the serial diagonalization. So it's not a surprise that it takes much more on the few gigahertz KNL cores rather than on the 1.4 gigahertz KNL cores rather than on the Broadwell. But there are some annoying situations where the difference is growing quite a lot, like D dot or DGR that are used in parallel diagonalization. But even worse, there are some routine where the difference is huge, and some helper functions of MKL, which are not so negligible, like, for example, this case, where the time on KNL explodes. And this is starting to be visible. Like, we do observe that FFT performs very well in both cases. Of course, given different technical environment of the two platforms, but some linear algebra routines are performing very well and are appearing as a sizable contribution in the timers of the applications. So, sorry, I'm quite late. I will be very quick on the last points. So to be able to identify these sort of unexpected results, and also to provide in the future, hopefully, an auto tuning of the parallel execution parameters, we are making a performance model which takes as input the details of the simulation that you are going to execute with Quantum Espresso and some details on the machine that you are going to use, and it provides an estimate for the time that the simulation will take. And for example, it's an early stage of development, but it's already able to correctly guess. So that true is the blue here and orange is the estimate. I'm sorry, these colors are wrong here. So they exchange. I'm sorry about that. But in any case, what matters is that you also have the correct identification of when it's convenient to run on, for example, on Broadware, or running on 2 cores on KNL. Well, of course, this is also important for co-design and to understand how the performances will change as you change one of these parameters. Okay, so, well, very quickly through the conclusions. Cache mode is working great for PW. We have problems with scattering in the new FFT that is now available in Quantum Espresso. Some MKL functions are unexpectedly too slow on KNL and should be fixed, and that could really shrink sizably the time of the simulations. And finally, well, the performance modeling and also mini benchmark applications were very useful in doing this analysis. So this is it. Thank you for the attention.